let me record that too. Okay. In the first part, it was quite constructive and efficient in order to define the complex power. Now we continue to analyze the power calculations, this time on the mutual inductance concept, because we can apply the power concept to any configuration. One of which is the mutual inductance, of course. Okay, and I wanted to cover one of the mutual example as well for the power calculations. Nothing different as long as you construct the circuit in the phasor domain. Then you'll be able to calculate not only the circuit parameters but also the power calculations. As usual, it is no surprising. So this is the example now. We will be concerning. Let me see. Okay. This is nice. Lots of dots on the terminals. We have to consider the dot conventions. Well, it is easy for us because it is already constructed in the phasor. What is the important thing? We are gonna define two currents. One of them is IG, the other one is another mesh current. We are gonna define two mesh currents, right? And then over the mesh currents, we are gonna follow the dot connected terminals. In each dot connected terminals, we are going to induce proper related voltages at the same time. I'm sure you remember this concept as well. What is the question then? Find this FT right here will be ohm. Find the average power delivered to the 8 ohm resistor. I'm going to correct that too. In the circuit in the figure, find the average power developed by the ideal sinusoidal voltage source. Another important outcome. Find ZAB. So this is the overall impedance seen by the terminals AB. And show that the average power developed equals the average power dissipated. So it's another important concept. I am going to define, well, this is the results, of course, but I'm going to define two mesh currents. One over short, I2 will be over load side, 8 ohm resistance. So IG and I2 will be two phasors in that sense. Through the animations, I haven't seen those, so they are left over here, but these are going to be the result anyway. What are the equations for part A? I have to write the equations from both sides. I have to follow each component and the mutual inductances. So I have such a long term. Well, 2IG, J10 IG, J14. This is the first mutual. IG minus I2 minus J6 I2. And then this is going to be the all induced voltages and the appeared voltages on the first mesh current. Second mesh current over the load side, we have defined that by I2. I'm not going to go to details, you see, because this is the topic for the first term. You should know how to write the mutual inductance induced voltages over each element, especially what was the main rule. If you are entering the dot line, it is going to make the other dot line positive or vice versa. And then you have to define the voltages. What is the voltages on any inductive component? J omega M or L and the current over that. So this is the proper two mesh currents that you have to consider. And then look, in this set of equations, it only depends on I2 and IG. So we have two equations and then two unknowns, and then I'm sure that you will be able to solve that. IG is 20 minus J for ampere RMS. Why? Because source is RMS. So all the outcomes from now on will be RMS values. So IG and I2 can be calculated properly. I2, by the way, by terms, is just the resistive. There's no imaginary part on the complex element. Anyway. So
Couple connections are ideal, right?
Sorry?
Couple connections are ideal, right?
Yes, yes, yes, yes. Yes. No, not ideal. Real transformers. If you remember, for the ideal transformers, we have a number of turn rates. You remember, yes? So we have real transformers rather than ideals. In ideal transformer, we don't have any internal resistances. Some self-inductance goes to infinity, so on and so forth. So this is not the case for this particular example. Okay. All you have to do is just to write the cases. We don't care about the not care, but we don't put the number of turn rates into the calculation for this particular example. Okay, 8 ohm is easy because I2 magnitude of I2 is 24. We are gonna get the square of that. 22, this is the magnitude, and 8, this is 4,608 watts. Is there any 1 over 2? No. Okay. So it is dissipating the power as usual for the resistance. For part B, we have to check out. Let me see. Find the ratio block by ideal. Okay, yes. Okay. So 272 multiplied by 20. Okay, this is 5,400. There are different ways. You can multiply this, and then real part of the complex power will be average power. So that's why we are multiplying it by 20, because this is going to be real part of the complex power. How can you calculate the average power on the source? You are going to get the, well, you have 272 volts right here, and then complex conjugate of IG, right? It means 20 plus J4. That should be multiplied. You are going to get the complex result. Real part of the complex result will be average power. So this is 5,440 watts. What is the impedance seen from the terminals A and B? VG over IG in phasor, of course. We are subtracting 2 ohm because 2 ohm is left over from terminals A and B. So this is going to be the result. And then this is going to be 11.38. Okay. Then I check out this one. This is the magnitude. This is the phase angle. And then this behaves like inductive load between terminals A and B. This is what I can say about this. It's quite close to 1 at the same time. What about the average power dissipated at 2 ohm. This time, Ig square, the magnitude of Ig square. Look, it is for tau. The current could be in both direction. However, when you get the square right here, you are not gonna get any negative sign. So the resistance cannot generate power, only dissipates power due to this square part. Okay, and the absolute magnitude. Anyway, what is the total dissipated power right here? 832, which is the 2 ohm resistance dissipation. 4,608, this is for the load side. In between, we have all inductive elements, so there is no average power dissipation on this T-shaped branches. Okay, oops. So this is the total verification. Developed power should be equal to, what is the developed power here? Part B shows that. This is the average power developed by the source, and then this is the average power dissipated in the circuit. So they are going to verify each other in that sense. Okay, last part that I would like to mention, maximum power transfer. We are revisiting this quite a lot. We know that from the first term that the maximum power transfer condition is this. What is that? It should be equal to Thevenin resistance, isn't it? If it is the simple resistive circuit, it should be equal to Thevenin resistance. Then they are going to be the same concept. We are going to find out the Thevenin equivalent circuit again. However, this time we are going to interested in the Thevenin impedance. So we have two parameters to be optimized for the maximum power transfer. I would like to tell you one more. This is not the maximum power transfer, actually. Now we know quite a lot about power calculation. It is actually maximum average power transfer. You should understand the reason, because the average power is converted to work. You would like to have the maximum average power drawn from the circuit. That's why, that's the basic optimization that we have to share about this. When we talk about the maximum power transfer on this stage, you can be sure that actually we are talking about maximum average power transfer to the load side, from source side to the load side. Okay. We are gonna divide that into two parts. One about if it is unrestricted, which means that I can use any load from -infinity to plus infinity. Let's say resistance cannot be in this particular option. Let's say plus 0 to plus infinity. Let's say. The other one is restricted. You might not have every type of load. Let's say you might have some range of resistances and some range of reactances, and then you might be able to be expected to get the best out of this load restrictions instead of in terms of transferring the maximum average power. So restricted optimal load is quite important issue to consider. As usual, this is the circuit. In this left-hand side of the terminal A and B might be the complicated circuit, right? This complicated circuit should be converted to the simple one, basically. This is the first step. You have to convert that to the Thevenin voltage, open circuit voltage, and the Thevenin impedance in this case. When we talk about the Thevenin impedance, it is the complex number. You know that. It's a kind of combination of resistance and reactance. On the other hand, ZL is the load side. It should be, again, complex number, combination of some circuit components. Well, let's make it a little bit more open form. Thevenin impedance could be Thevenin resistance and Thevenin reactance. At the same time, load impedance could be load resistance plus, these are the model of the load, and load reactances. What is the current defined on this mesh? Thevenin voltage should be divided to the summation of these two impedance seen in the circle. Okay, let me write this in open form again. VTH over resistive values should be combined together. Reactances should be combined together. Okay. Forget about the zero at the bottom line. We will come to that one. The average power now should be calculated over this combined equation. This power, it is going to affect the power calculation. How can we calculate the power? Okay, we have the current there on this mesh. This current should be squared and then multiplied by the resistive component of the impedance. This is how we are going to define that. Okay, the current there, that should be the magnitude of square magnitude of the current. As usual, you remember our previous discussion, yes? If we have the current in our hands, current can be defined over the serially connected load impedance. And then this is that RMS value or the peak values? RMS values, of course. This is the expression for the RMS value. So Thevenin voltage should be in RMS, basically, if it is the case. Right here, now I'm gonna define the magnitude, square magnitude of current. VT, RL is that one. However, the rest is the first the current magnitude, then getting the square. So the square root at the denominator will be cancelled out. Now, first task is take the power expression, take the derivative in terms of reactance, because now we have two variables. One is the resistance, the other one is the reactance. Both of them are quite effective on the maximum average power optimization. How can we understand their effect? We have to take the derivative in terms of that variable and then equalize it to zero. This is how we are going to find the optimal point. Now I'm taking the derivative. If you take the derivative, first numerator, denominator minus numerator divided by the square of whole term, denominator term. Of course, when I say numerator, denominator, I'm not saying we have to take the derivative in that sense. So I'm just bypassing some words. But when you have the derivative of the division, you are going to get this, and then you have to equalize it to zero. What is it? That what denominator will be zero. This upper term should be equalized to zero. What do you expect from there? XL should be minus XTH, of course. This is that's a simple outcome. However, don't forget that this can be implemented only when we have infinite sources. or there is no restriction on the source. Suppose that you have all type of reactances, then you can do that. If we have a limitation, we should be close to XTH. Not maybe exactly the same, but close to. What about the resistive case? I might, for the first case, I might try to make it the expression without any limit. But anyway, first, let me make the derivation again. This time, not for XL, for RL, another derivation. I'm taking the derivative of the power, average power, in terms of what? Resistive value of the load. When you do so, you are going to get this type of expression again. Make it to equal it to 0. So we have the upper part right here. What am I going to do? I'm going to take the real alone because I'm looking for the proper RL. Then RL will be this one. RL is equal to RTH squared plus XTH plus XL squared, and then of course square root again. This is 4, but look, this is the real result. Don't forget that. Keep that in your mind. This is the real result. If you use the first condition, when we don't have any limits, then it will become, when you evaluate this, it will become RL is equal to RTH. And then ZL in general, complex conjugate of ZTH. Why? Because XL is equal to minus XTH. Okay? So, if you don't have any limits, if you have the free choice for your impedance, right? You have to choose your impedance as a complex conjugate of Thevenin impedance. Then you can be guaranteed that you are going to get the maximum power transfer from the circuit or from the source. Okay. Without restriction on ZL, we determine if you don't have it, we are going to determine this ZL, the maximum power, blah, blah, not too much. This is the example. I'm trying to sort out this type of text there. Anyway, this is the example without any limitation, right? It is easy. First, we are going to use the source transformation. Okay. This is going to be current source first. Then there's a parallel combination of this. So we are going to reduce it to this circuit right here. And then I'm going to look for the Thevenin voltage here, because I have to find out the Thevenin equivalency. ZTH is going to appear when we fill the source. So it is 4 plus J3 will parallel to minus J6. Then this is going to be the Thevenin impedance in the circuit. You can find Norton current, which is the short circuit current here. It is just a plain division. 16 should be divided by 4 plus J3 for the short circuit current. Okay. So we are going to use the relation between Norton equivalency and the Thevenin equivalency, or Norton short circuit current and the rest. We Thevenin, therefore, is short circuit Norton current multiplied by the Thevenin impedance. We have already found that. So this is going to be the Thevenin voltage. Good. Both of them have been calculated easily. We can continue now. Look, this is the Thevenin equivalency. I'm just going to place all the known information to the equivalent circuit, right? Now I'm going to connect the load to the circuit for the maximum average power transfer. You agree? What is the condition? That L should be complex conjugate of the pH. Look, 5.76 is the same. However, reactance will be the opposite side. And now look, they cancel each other. So you are going to get the maximum current from the circuit if the reactances will cancel each other. Otherwise, there will be the complex side of the total impedance, and then it's going to reduce the magnitude of the current. This is, you see how useful to use this optimization in the maximum power transfer. Okay, this is the condition now we have applied. This is the current that we draw from the circuit, from the equivalent circuit. When you evaluate that, you are going to have 1.67 ampere in magnitude. All other variations will decrease the current, no matter what. What is the magnitude? 1.67. Well, you can convert that to the RMS value if you like. If you like, you don't. However, you have to use 1/2 for the power calculations. It is up to you because you are going to get the square of this value. Either you use the peak value with the 1/2, or you are going to use the RMS value. This time you have to convert this to RMS value. Here we go. Pmax then, I RMS square multiplied by RL. Okay, when you overlay that, 8 watt will be the maximum average power transferred to the load. Okay. What about when you have the restriction? You are going to see the restriction one on the blue highlighted term. Again, we are going to seeking the maximum average power. However, we have restrictions now. RL is between 0 to 4K ohm. This is another example. XL inductive value is 0 to minus 2K ohm, which is capacitor. It says that I have only capacitive components up to minus 2K ohm. Okay? So, when you check out the circuitry, this is the Thevenin impedance found already as 3K resistive value and 4K inductive reactance. When you check out the load should be capacitive, basically, because it should be complex conjugate of Thevenin impedance. So that's why I put here the capacitive symbol. However, this capacitance is not freely chosen. There's a restriction upon that. Okay. Without restriction, it should be simple. We are going to choose 3K ohm for the load, minus 4K ohm. I should put here K ohm is just downline. Minus 4K ohm for the capacitive reactance. When you calculate the current and now calculate the power, you are going to get 8.33 milliwatt. This is the maximum power that you can get. Yes? Okay. This is the power plane showing the optimal power result based on horizontal and vertical axis. You have to read load resistance from 0 to 5 k ohm, minus 5 to 0 k ohm, which means that there is no limit on the reactances, and then you can manage the optimum power, which is the maximum average power transfer, on this blue dot here at the let's say reddish or dark reddish area. Okay, actually it shows that the optimization problem in this plane. However, this is white dash line here is the limits that it's given to you. So you cannot really go into this optimal point. So you have to choose best reactance and the best reactance and the resistance to get closer to that optimal point. Okay. Look, this is the then optimization problem when we cannot really provide this equality. What was the RL term for this? RL should be RTH, XTH plus XL. When there is no limit, this is going to be 0. This reactive part of that square root will be 0, and then RL will be RTH. However, it's not the case for this one. Okay, let us see. Now I'm going to iterate that. RTH is 3K. However, minimum reactance that I can choose is minus 2K. Actually, I was trying to choose minus 4K to eliminate this part, but I was not able to do that. So I'm going to evaluate this at minus 2K. Then RL should be chosen as 3.6K. I might have restricted on the resistance as well. So I could probably I would have chosen my resistance closer to 3.6 as well, depending on the ranges. Okay, we don't have the restrictions at least on the 3.6 k ohm, so I can choose that blue line right here. Okay, and minus 2 for the reactance. This is the minimum reactance, or on the minimum axis. More negative side, to be honest. So this is the choice. This is the point that I can come closer to the point. So I can now calculate the current 10 volts, like previously defined. 3K plus 3.6K. So this is gonna be 6.6 K ohm. Plus, now we have reactance due to limitation. J4K minus J2K. So it is going to be J2K. So limitation is going to affect my resistance and then my reactive side. Then magnitude of the current is 1.45 milliampere. And then maximum power that I can draw is going to be this one, I square over RL. Let me put it into the term, then the result will be 7.57 milliwatts. Right here, this is the closer point to the overall optimal power transfer. So there is an effect of restrictions on the power transfer. This is the best way to view. Last part of my example. This is the example that I would like to go a little bit fast. Just I'm going to show you how you can solve it rather than having the numerical values. However, I'm going to show you the numerical values as well. Look, this is the question. This is kind of exam question, to be honest. There is a dependent forces, independent forces, powered by the RMS voltage or sinusoidal force, reactive values, and right here we have the resistance. What does it mean? If the resistance is just a simple resistance, it means that there is a restrictions on the load. Because in load side we might have the reactive values as well. If it is variable resistance from 0 to infinity, although there is no limit on the resistance, it means that there is a limit on the reactance. Okay, the variable resistor, blah blah. This is the text. What is the value of our own in the maximum average power transfer? Calculate the average power delivered to the output resistance. Now, resistance is replaced by the variable impedance. That note this time, it means that part C is clicking this circuit into the limitless one. No limit upon the load. Part C is without any limit. And part D is the most difficult part. What percentage of circuits developed power is delivered to the load Z0 or Z output? So this is the question generally that you may face. What is the first thing? We have to find out the Thevenin equivalency, isn't it? If it is Thevenin equivalent, this current is already known, and then there is only one unknown, because first node is known of the source voltage. This V phi is not known. So there is only one unknown in the circuit. Write it down. V phi minus 100 over phi, V phi over J phi, and then the current is already the same, 1 point V phi. So there is only one unknown. You can calculate that. V phi is 40 plus J80 volt RMS, because force is RMS. Now we can calculate VTH. For VTH, you have to write the Kirchhoff voltage law on this final loop. So this is V5 plus the voltage drop on the minus J5 ohm reactance here. The current on this one is the dependent source current here. So it's easy. 80 plus J60 volt RMS will be the result because we know the V5. Short circuit current now. This time I'm gonna short circuit those terminals and then find the short circuit current. The other way to find is to use the test voltage, of course, but a little bit more calculations required. This is the easier one. Short circuit current will be the current of summation of two currents, one from V5 over minus J5 ohm to the ground. The other one is dependent source current. When we do so, it is again related to V5. So we have to find V5 again. V5 is node at the middle, voltage node voltage at the middle again. writing the node voltage, V5 minus 100, you have to write it again because the circuit is drastically different. V5 over J5 and V5 minus J5, because this is the last node is also grounded now. You don't need to write more equations. That will be good enough. So you calculate V5, 100 volt, nice. Then find the short circuit current now. Because in the first equation, we have already found it. So this is 10 plus J20 ampere RMS. When you find Thevenin voltage and short circuit current, the Thevenin impedance is quite easy now, just the plain rate. So 4 minus J2 will be the Thevenin impedance. Well, our output resistance should be magnitude of ZTH, because if you remember, RTH square plus XTH square root. So actually this is just the magnitude of ZTH. There is no XL, there is no load reactance. When you evaluate this to the proper equations, you are going to get the last equation, S447. Now, for part B, we are going to calculate the maximum power. In order to do so, use the Thevenin equivalency and then add 4.77 or square root of 20 to the circuit. Then you are going to get the average power as 590.17 watts. Part C, now we are going to replacing the output resistance with limitless impedance. So reactances will cancel each other. The result will be at the denominator is 8. Summing up the resistive value, that's it. So you can calculate, due to this current, you can calculate the average power as 625 watts. Look, this is the optimal power actually. The first power is the closest power that we can come closer to the optimal power. This is the average maximum average power that you can draw without any limit at part B. Sorry, part C. The power that you found at part B is the one that you come closer due to limitations. Part D, now you add the load 4 ohm plus J2, because our Thevenin equivalent is 4 minus J2. So complex conjugate load is added to the terminal, to the right-hand side. We know that we know the current. If we know the current, we know the voltage as well on this node, output node. Then you are going to calculate V5 again. This V output, yes, this V output should be V5. You have to correct this one too, because the output voltage is already calculated as 25 plus J50 here. V5 then can be calculated as 50 plus J25 ohm. This node, this middle node, is the so critical node. Once you calculate that, you can calculate all currents in the circuit. Okay, so when you are able to calculate all currents, you have to calculate two currents critically: one on the source, dependent source, one on the independent. Because there are only two sources that can generate the average power. Okay. So I can calculate Ig over the source, IR plus 0.1 V5, This is 15 minus J22.5 ampere. This is the current developed by developed by the voltage source. So it is easy. It was 100 volts. How can you define this minus sign? Due to sign convention again, because it is going upwards. So it should be negative sign. There is no 1/2 because it is RMS values. And then you have to put here IG complex conjugate value.
Hocam, could you please remind the questions part of D?
Okay,
It's actually hard to remember.
Sure. Devrede load'da tüketilen average power ile devrede üretilen average power'ın oranını soruyor. That's the rate between generated power by sources and the dissipated power on the load side. We have already calculated the absorbed power on the load side. Okay, now we are trying to find out the generated power. In order to find the generated power, we have to calculate the average power on two sources. One is the independent source at the far left side. The other one is the upper part dependent source. Now I'm calculating first is 1500 watts. This is for the independent source, voltage source. This is minus 1500. If it is minus, so it is developed. Here. What? This is the developed one. However, what about the dependent source? I haven't calculated that. You are going to calculate the current on this you have to calculate the voltage on this current source first. Then again find the complex power on the dependent source. But I have calculated that already for the current source. Look, first part is positive. Talha, if it is positive, what does it mean? It is absorbing.
Evet hocam.
Average power. So we are not going to put this into a calculation of the generated power summation. Good. So what is the rate then for the delivered power? 625 watts on the load side. Dissipated power 1500 watts is the generated power overall summation. This is the rate. So 41.67% of developed power is absorbed in the load side. This is the maximum that we can transfer from the circuit. Okay, any question?
Hocam, o zaman hani gerçek hayatta ideal komponentler yok yani. Sonuçta bir şekilde depolanan enerji cihaz kapatıldıktan sonra ısıyla veya başka bir yolla boşaltılacak bu reaktif elementlerin içinde depolanan enerji. O zaman bu reactive power waste of energy mi oluyor direkt?
Yok öyle. Buradaki reaktif power diyorsun. O devrede magnetization için ihtiyaç duyulan gerek kapasitansta gerek de depolanan enerji. Ama onun depolanan enerjiyi ne kadar düşük tutarsa, mesela bir makinenin sarımlarını egzalt etmek zorundasın, değil mi? Yani sürüm akımları vardı, bobin akımları. O makinede diyelim ki olarak kalır. Magnetic field olarak kalır makinede. Peki R dediğimiz tanımladığımız load direnci ne? O da işe dönüşü. Mesela harekete dönüştü. Yani illa bir direnç olarak ifade ettiğimiz şey illa bir direnç olmak zorunda değil. O yapılan işin model karşılığı da olabilir sistem olarak. Anladın mı ne demek istediğimi?
Yo zaten ben direnç olarak modellediğimiz şeyi
Şimdi
anlamıştım da.
kimisi elektrik alanında kalıyor, kimisi manyetik alanda store edilmiş oluyor. Şimdi kapasitans katmanın sebebi burada negatif reaktans ürettiği için bobinlerdeki pozitif reaktif harcanan gelimi tavrı kompanze etmiş oluyor. Biraz yoruldum, kelimeler tam çıkmıyor ama doğal olarak sen devrede store edilmiş enerjiyi minimize tutmak zorundasın çünkü para veriyorsun soğutma.
Ha onu diyorum işte. O zaman işte ne deniyordu? Q değeri aslında bizim boş harcadığımız enerjiye eşit oluyor değil mi direkt?
Vallahi bir yerde öyle denebilir. Store edilmiş oluyor. İşe dönüşmüyor.
İşte cihazı kapattığımızda ama boşalmayacak mı bir şekilde? Boşa gidecek yani. Öyle düşündüm de.
İstemsiz bir takım hareketlere dönüşebilir. Onu kullanabilirsin gerekirse ama çok kullanılacak kadar önemli bir şey olmayabilir.
Peki, teşekkürler.
Yani uzun vadede periyotlar üzerinden bakar. Peki, bugünlük bu kadar diyelim. Benim aklıma gelip de söylemek istediklerim bunlar. That's all for today. Next week, I'm gonna share this material with you because I have just completed to prepare it. So I'm gonna share this PDF form, share this material in PDF form in Star System. And also, a little bit later, maybe I can combine a video series and then you can also follow those videos when you are preparing to the exam, okay? That's all for now, folks. I'm gonna see you next week.
Hocam çok küçük bir soru sorabilir miyim?
Okay, let me paylaşayım. Okay.